All right, so let's have a discussion today about concentration. When we have materials in solution, which is the subject of this chapter, we need to still have a way to count the number of molecules. Now, we've spent a lot of time this semester first learning how to count molecules by their mass, because you can't count individual molecules, but you know what the mass of 1 mole of a molecule is. So you measure the mass of however many moles you have, and then you know how many molecules there are. Then you can write balanced equations and make predictions about theoretical yields and figure out what reagent's going to run out first by keeping track of how many moles of material are there. So all of that is basically counting molecules. By now being able to do that in solution, we need to find a different way to account for the number of things that are in solution. That's what concentration allows us to do, right? It's a way to measure the quantities of substances when they're in solution. And here's just one example. We don't need to go through this. I'll just say, when we balance this equation, and this one looks balanced to us, right? This is sodium chloride in aqueous solution. The solute is what? What's the solute here? You have to remember your definitions. What is a solute and what's a solvent? What's the solute? It's sodium chloride, NaCl. And what's the solvent? Water, because it's an aqueous solution. Water is the solvent. So we need a way to be able to count how many moles of NaCl are there, or how many formula units are there. Right? We need a way to count moles, or just to count. Well, I'll say moles, that's fine. All right, so there's several ways to do this. I'm going to talk briefly about 2 of them, and then we're going to focus on the 3rd one. The first one is parts per million. You hear this term a lot, especially when things are not very abundant. Right? This is used for very dilute solutions. Like, for example, when you're talking about the concentration of carbon dioxide in the atmosphere, and if you're having a conversation about global warming and rising CO2 levels, well, if you look back on my original definition here of a solution, and we used air as an example, carbon dioxide is much, much less than 1% of the total. So if we put that in a number, it's going to be a really, really small number. So instead of expressing that as just a decimal number, a fractional number, we're going to express that in parts per million. It just makes it more convenient to be able to express a very, very small number in a more manageable way. So if it's dilute, it's going to be a very small number. So we take a look at how many parts are there for every million parts. Now, if I were to say, take a percentage instead, what does percent mean? Percent. Per 100, right? Percent, that's what the word means. So if percent, and here's the symbol for percent, okay? So we know that percent means it's some number out of 100. Okay, simple enough. And if I want to say, let's say I have 25%. If I tell you I've got 25% of something, that means I have 25 parts per 100. 25 parts per percent, right? 25 parts per 100. Well, it's the same logic with parts per million, except now it's not out of 100, it's out of a million. Okay, so the symbol for parts per million is ppm. That simply means that we have so many parts per million, which is 10 to the 6th. So if I tell you that we have 25 parts per million of something, that means we have 25 parts per million. That's going to be the same. Here, let's write that up here. 25 per 10 to the 6th. Now you can punch that in your calculator and get a number, but I'm just going to express that without showing it in scientific notation. When you divide something by 10 to the positive 6th, that's the same as multiplying it by 10 to the negative 6th. That's just how you work with exponents. So this is 25 times 10 to the minus 6. If I were to express that with decimals, you'll see why we want to do this in parts per million. I have to now count all these decimals. So if I start here and work my way to 10 to the minus 6, that would give me 0.00000. 1, 2, 3, 4. That would be this, right? 1, 2, 3, 4. See, I have to go back and check and count. So that's why it's more convenient to express this number as 25 parts per million instead of trying to manage all these zeros, or put it in scientific notation for that matter. Another way you see concentration talked about a lot, especially not in the science laboratory, but if you go to the hospital, for example, and they need to hook you up to an IV and rehydrate you, they give you like a 5% saline solution. Does anyone know what saline is? It's what? It's sodium chloride. Saline is a sodium chloride solution, right? But if you go to the hospital, they're not going to say, hook this patient up to a 0.8 molar solution of sodium chloride. No, they're going to hook you up to a 5% saline solution. So let's talk about that a little bit, right? Let's say in the hospital, we're going to have a 5% saline solution. Well, this is a percent mass per volume solution is what we're talking about here. It's still a percentage, but it's now the percent of some amount of mass per some volume. Okay, so this is going to be some mass, X mass. It's not Christmas time, but it's some X mass per 100 of volume. Well, 100 what? Okay, this is going to be an aqueous solution. If you remember the density of water, what's the density of water? 1 gram per milliliter. Okay. Well, this mass is in grams. So if I want to have the mass of sodium chloride in grams divided by 100 what? 100 grams. That's going to give us our percent. But this is mass per volume. All right. But we know what the mass of 100 milliliters of water is, right? That's 100 grams. So 100 milliliters of water is equal to 100 grams. So in this case, the percent solution is going to be some mass. So X mass of your solute per 100 milliliters of water. Because these are all aqueous solutions. That's the whole subject of this chapter. So that's why it's divided by 100 milliliters of water, because that's really giving you 100 grams of the solvent. All right, so let's take a look at that 5% saline solution. That means we have 5 grams of sodium chloride per 100 milliliters. That's what that means. 5% saline solution. So we could do some math with this. We can say, all right, how much sodium chloride do we need to make 2 liters of a 5% saline solution? Well, we know the math for what a 5% saline solution is. If we had 100 milliliters of it, we would need 5 grams, right? But now we don't want 100 milliliters, we want 2 liters of it. Well, let's figure out what that is. For some reason, I want this to be 2.5 liters, sorry, just because that's how I have it in my notes. All right, so let's solve this for 2.5 liters. So just take a look. This is your defined ratio. In a 5% solution, it's 5 grams per 100 milliliters. Well, now we no longer have 100 milliliters. We're going to have, how many milliliters are we going to have? 2,500. So solve for X. It's a simple ratio. You can cross multiply. And this is easy math. All right, when we go and solve for that, let's just solve for X. X is equal to 5 times 2,500 divided by 100, which gives us, let's see, when I did this, 125 grams of sodium chloride. Okay. So if you were in a hospital setting and someone told you, go make a 5% solution of sodium chloride, you don't have time to go look at the periodic table and figure out the molarity and all this stuff. Oh, oops, I said that word. I haven't defined molarity yet. You just want to make a 5% solution real fast. So you do the math, you know that you need to take 125 grams of sodium chloride and dissolve it in 2.5 liters, and boom, you're done. Okay. But that doesn't tell us anything about how to really count the number of moles in here. We're just making a solution. I'm going to show you this by moles in just a second. All right. So you tend to see this in a hospital setting because it's very easy to make. This is also useful because it's independent of the identity of the material. I mean, that's kind of what I was talking about before. You don't have to go to the periodic table and figure out what the molar mass is, and then how many of those moles you need to put in this 2.5 liters. If I needed to make a 5% glucose solution, right, it's the same thing. I'll take 125 grams of glucose and put that in 2.5 liters. If I need a 5%, I don't know, make up your compound, whatever, okay? It's independent of the identity. We're just making a 5% solution. So all we care about is the mass of whatever it is divided by the mass of the solvent, or in this case, milliliters of water, okay? Now, that's in the hospital. We're in the laboratory, all right, doing science, so we're going to work with molarity. And molarity is how we can actually count the number of moles directly, but we need to do a little bit of work to get there. So the definition for molarity is moles of solid divided by liters of solution. We use a capital M for our symbol for molarity. So this, you've seen this in lab all the time. All those reagents that you're taking in your lab experiments, like 6M HCl, right? That M means that you have 6 moles of hydrochloric acid per liter of solution. The word we would use here is a molar solution. Really what it is, it's moles per liter, okay? Moles per liter. You usually don't write out moles of solid per liters of solution. It's just moles per liter. And you know how to calculate moles, and you know what liters are. So let's go ahead and see what's the molarity of our 5% saline solution. Okay, we know that when we make a 5% saline solution in 2.5 liters, we need 125 grams. So here's our 125 grams of sodium chloride. And now we need the molar mass because we want to know how many moles of sodium chloride that is. So you might remember what the molar mass of sodium chloride is because you use it a lot. And if you don't remember, you've got a periodic table in front of you, right? Sodium is 22.999 or 999 or 990. Oh, that looks like 9. Let's just say 99. I don't want to think about it this morning. And chloride is 35.453. So 3, 4, 5, 14, 14, 58.44 grams per mole. Okay, so where is the 58.44 going to go? Is it going to go in the numerator or the denominator? The denominator. Always do it this way. We're going from grams to mole, right? Or maybe some other thing, we're going from moles to grams. I've told you this several times, but students will still do this. They'll just remember some rule that, oh, if I'm going from grams to moles, I divide by the molar mass. Or if I'm going the other way, I multiply by it. And come test time, you're going to forget which way it goes. So you do it by dimensional analysis, you never have to remember it. you all know to recognize that the 58.44 goes in the denominator. That's per 1 mole. This is the molar mass. It's just the inverse of the molar mass. That's the same as taking grams and dividing it by the molar mass. Okay, but now you don't need to remember that. Okay, this gives us moles. And if I work that math out, 125 divided by 58.44, and I get 2.14 moles. That's moles of NaCl. Now I want to calculate molarity, so I need to know how many liters is that number of moles in. That's going to give us our concentration. Okay. Well, we're putting this in 2,500 milliliters. That's 2.5 liters. Now we need to work in liters. Molarity is in liters. Okay. So that's in 2.5 liters. So our molarity is, I divide this by 2.5 and I get 0.86 molar. I put a capital M. That's the symbol for molarity. And if I were to say this in language, I would call this a 0.86 molar solution. And I can also interpret that to tell me that there are 0.86 moles of NaCl present in every liter of solution. Okay? So now we can count the number of moles of what we have based on the volume. Using this, now molarity, this is a conversion factor. Anytime you've got a quantity that's something per something else, like the molar mass, right? 1 mole per 58.44 grams of sodium chloride. That's the inverse of the molar mass, but it's a ratio, okay? But we can use that as a conversion factor. All of these can be used as a conversion factor. Also, a conversion factor. Okay, so now you know what the molarity of this 5% solution is. Now, in this case, molarity is not independent of the identity. Okay, a 5% glucose solution is going to have a different molarity than a 5% saline solution. Okay, because molarity is based on moles, and the percent solution is based on mass. All right, so now that you know that, maybe you already knew that, let's practice some of the simple math that's involved with making these conversions. And we're going to do this all by dimensional analysis. I almost might want to just let you try these on your own, but just for the sake of time, I'm going to lead you through these, okay? But we'll try to do it slowly. Maybe I'll give you a chance. Did you all bring your calculators with you? Even if you don't have a calculator with you, you should be able to set these up, all right? So I'll do the first one for you. And of course, normally when I do a slide like this, they get progressively more difficult. So that means the first one is the easy one. Calculate the molarity of a 2-liter solution of 5 moles of sodium hydroxide, NaOH. Well, that's just simply the definition of molarity. Molarity is moles per liter. So we're given 5 moles of NaOH divided by 2 liters. So that's going to give us a 2.5 molar solution of sodium hydroxide. So that would be written as 2.5 molar sodium hydroxide. But once again, that means that we've got 2.5 moles per liter. That means we can take any amount of that and figure out how many moles there are present in that any given amount. So for example, here, this one I'll challenge you for. How many moles of sodium hydroxide are present in 2 liters? It's not a trick question. You already have the answer right here in front of you, right? That's the question step. I should specify 2 liters of a 2.5 molar solution. This is typically not just how you're presented it as a question, but when you're working in the laboratory. This is what you do. You take 2 liters of a 2.5 molar solution. You did this, in lab all the time. You go to those materials and you take a certain volume, and there's a concentration on that volume. Well, we're telling you how much volume to use because we know how many moles that is. But now you know how to calculate that. It's really just what I did here in blue, working backwards. You start with what's given. We're given 2 liters. Normally, the given quantity is the amount that's measured, not the conversion factor. Right? Some students will say, well, I'm also given 2.5 molar NaOH. Yes, but that's the concentration. That's moles per liter. So you do need to learn how to distinguish between what's given to you as a measurement that you need to convert to something versus a conversion factor that, yes, you're also given that in the problem. So we start with what's given. What's measured is 2 liters. We're going to use a conversion factor to get that into moles. So we have liters now in the denominator, and we have moles in the numerator. And how many moles are there per liter in a 2.5 molar solution? We have 2.5 moles per 1 liter. That's going to give us 5 moles, which of course is what we started with in the problem. Okay. Now this is all molarity. Even though I told you about working with percent solutions and parts per million, everything else that we're doing in this chapter, we're going to work in molarity. Okay. So now I'm giving you a mass of sodium chloride. And we already calculated what the molar mass of sodium chloride is. So I'll just remind you, that's 58.44 grams per mole. All right. Now, see if you can figure out what the molarity of taking 95 grams of NaCl and putting that in 3 liters of water. Go ahead and work that out. And then we'll see how well you do. Raise your hands high with your fingers with 1, 2, 3, or 4, what you think the answer is, nice and high. I see lots of everyone's saying the same thing, which is 3. Very good. I believe the answer is 3. Let's go ahead and work this through. So we start with what's given, 95 grams of NaCl. We now need the molar mass, which is going to be 58.44 grams of NaCl for every 1 mole of NaCl. That's going to give us moles. So you could calculate moles right now and then divide it by the volume, or you can just say, I know that when I do that calculation, that's going to give me the moles, and so I'm going to be dividing that by the volume, 3.0 liters. And now I have one expression. I can do it all in one calculator expression, or you can divide it into 2 steps. That's perfectly fine. I'm just showing you a different way to do the math. So let's just do it. Let's just do it the methodical way. Let's just calculate the number of moles. 95 divided by 58.44, 1.62. Now, the danger in doing it stepwise, especially if you write stuff down and then re-enter it in your calculator, is you don't want to suffer from early rounding error. And although we're not so hyper-focused at the moment on significant figures, a general rule of thumb that I use is to always carry a few more digits than you think you need in the end. And you always apply your rounding for significant digits at the very, very end. Now, you could also just keep this in your calculator, then you don't need to worry about it. But I'm going to purposefully write down a few more significant digits here than I really need. So I'll go to 5, 6 here. That's moles divided by 3. Now, of course, I've kept it in my calculator here, so I'll just divide this by 3, and I get 0.54 moles per liter. That's answer 3, which you all got correct. Very good. All right, here's a variation. How many moles of sodium hydroxide are in 10 milliliters of a 5 molar sodium hydroxide solution? So rather than spend more time, now that you're kind of getting a hang of this, I'll just show you the extra steps here. We need liters, but we're given milliliters. So you start with what's given, Now, some of you can probably do this in your head, and simple conversions like going from milliliters to liters. If you want to do that in your head, by all means, go ahead and do so. Just make sure you're very comfortable with that manipulation. I'll just be methodical and show it to you now. We're given 10 milliliters. I'm going to convert that into liters. So there's 1,000 milliliters in every 1 liter. Now I'm in liters. Now I'm going to use my molarity to convert that into moles. I know that for every 1 liter, we have how many moles? 5, because the molarity is 5 molar. So we have 5 moles of NaOH per 1 liter, and then that's it. That gives us what the number of moles are. So I don't even need a calculator for this one, because 10 divided by 1,000, that's 0.1. Sorry, 0.01. And 0.01 times 5 is going to be equal to 0.05 molar. And if I'm keeping track of significant figures, looks like the molarity is given to me to 2 sig figs. So I'm going to report this to 2 sig figs. That's how many moles of NaOH. No answer is complete without the units. It's a number and it's units. How many liters do we need to make a 0.2 molar NaOH solution if we're given 2.2 grams? So now we've got grams. So we need to do the conversion from grams into moles. We know we're going to need the molar mass of sodium hydroxide. Sodium is 22.99, oxygen is 15.999, hydrogen is 1.008. That gives us 17, 19, 19, 8, 9, 10. Okay, so we're given 2.2 grams. And always put your units in dimensional analysis. Take the time, because that's your way of making sure in the end that you've set it up correctly. If you can't check your own work, then you have no way of ensuring yourself against a careless error. And of course, if you do show your work and make a careless error, I can see your work, and then you get partial credit, usually, if I'm in a good mood. Okay. We need the molar mass, which we just calculated, is 40.00 grams of NaOH per mole of NaOH. And we have, this is the molarity that we want to get to. And we're asked how many liters do we need to get there? Well, if I do this calculation, I'm going to have moles, right? But I'm not going to do that, right? I'm going to show you the next term. We want to get to liters. So we're going to still use the target molarity as a conversion factor. However many moles of NaOH we calculate that we now have this term. We want to have the volume that gives us this concentration. We want 2 moles of NaOH per 1 liter of solution. That will give us the liters of solution that we need. And let's just make sure. We always start with what's given, and that cancels out with this conversion factor in the denominator. We convert that to moles of NaOH. And now in our molarity, every 1 liter contains 0.2 moles. That's our target. Well, this will tell us how many liters we need to get to that target. So that's going to be 2.2 divided by 40 divided by 0.2. And that gives us 0.275 liters. This is going to be liters of solvent. And if you wanted to put that into milliliters, that's fine. That would be the same as 275 milliliters. I would accept either one, of course, unless the question is specifically asking you to give the answer in one unit, in one particular unit. Okay, so here, once again, we're using molarity as a conversion factor. In this case, we're using the reciprocal of molarity, but that's okay. With conversion factors, you can use the reciprocal, because all you're doing is using it to convert from one unit to another. Okay. So that was a little bit of practice. So now let's take this one step further and talk about making dilutions, which is probably one of the single most, not useful, but what's the word I want? Frequent. It's the single most frequent procedure that most scientists do, is make dilutions. And the reason we make dilutions is because we want to make sure that our materials are good. Anytime you make up a new solution, you want to make sure that it's quality controlled. All right, that's what I mean by making sure it's good. You want to make sure there's no contaminants in there. You want to make sure the concentration is what you think it is. If you need to do an experiment every day, instead of making up a new solution each day and then doing all the quality control and quality assurances on that each day, you're going to be spending a lot of time each day doing the same procedure. So instead, what we do is we make a stock solution, maybe once a week. And that stock solution, that's the one with all the quality control. QC, quality control. And we make that, let's say, once a week. And then every day that you need to do the experiment, you make a dilution. And that dilution gives you what we call the working solution. And that's what you're going to do the experiment on. Because the stock is already quality controlled, you don't need to worry about it. You just go and you make a dilution in water. And now you have your working solution. So when I say stock and working solution, let me put some more terms to this. The stock solution is typically, well, not typically, it always is more concentrated. Because when you make a dilution, you're diluting it in a larger volume. So dilution means you're putting it in a larger volume. So the working solution is always going to be less concentrated. Some might say it's diluted, but that's defining what it is with the term. Okay, so now I'm defining the term with other words. If something's diluted, that means it's less concentrated. In this example from the textbook, you really can't see it very well. I should stop wasting slide space with this. Can you see any difference in color in these three? You're supposed to. This is supposed to be lighter. This is supposed to be darker. I can see it on my iPad. As you dilute something, it's getting less concentrated. And so in this case, if it's a colored dye, it's looking lighter. So here's an example I like using here. Let's talk about orange juice. Who likes orange juice? Raise your hand. Oh, seriously? Only a few of you? Who likes sweet tea? Raise your hand. Oh my goodness. More of you like sweet tea than like orange juice? You should really go back to the orange juice. Okay, but you're all familiar with it, right? Let's say you were craving orange juice. How do you make orange juice? Squeeze oranges, right? Right. Do you have an orange tree in the backyard? No. So how are you going to go and get orange juice? Go to the store, and what are you going to find at the store? You're going to find a carton of orange juice. You take it home and you open it up, you pour it in a glass and you drink it, right? So what you've just purchased at the grocery store is a working solution of orange juice. It's already, the concentration is the concentration that you want it at the time you're using it. It's not an experiment, and this time you're using it because you're thirsty and you crave orange juice, okay? So that's your working solution. Now, some of you may have some grandparents who make orange juice a different way. Does anyone know what I'm talking about? How? Yeah, so they take it's not a big bottle, it's like a can, right? You go to the grocery store, you can still find this in some grocery stores, frozen concentrated orange juice, right? Frozen concentrated orange juice. And it comes in like, the size of a soda can, and you open it up, and if you've ever looked at it, it looks like solid toxic waste because It's concentrated. So that beautiful orange color is really, really concentrated. And it's thick. It's goopy. It actually tastes really good, concentrated, because it's super sugary too, right? All right, but that is a stock solution, right? So the company that makes it makes their orange juice, they concentrate it, and they do all the quality controls and quality assurances on that. And then they ship it out to your grocery store, and then you buy it. You take it home, and then you take that frozen concentrated orange juice and you dilute it in a liter or two of water, and then you stir it up, and now it's ready to drink. Okay? So we can have another discussion someday about the cost effectiveness of shipping working solutions of orange juice to all the grocery stores, right? Because that's a larger volume, it's a larger weight, okay? Versus shipping out concentrated orange juice to everybody, and then you go home and then you make the dilution to the working solution when you're ready to drink it. But we don't have time for that conversation. But instead, I'm going to use that example then to get you to how we use molarity and dilutions in the laboratory and the simple math that's involved to make these calculations. It's just the same as I showed you earlier. These are just simple ratios. The equation is just simply M1V1 is equal to M2V2. It's very straightforward. It's the molarity and the volume of the stock, right? So this is the stock concentration. And we're going to take some small volume of this. There's a name for that, the small volume of a concentrated stock. Does anyone know what it's called? Does anyone, before I tell you what it is? I'm just curious. It's all right. The small volume, it's called an aliquot. You may hear that term from time to time. We're taking a small aliquot of our stock, and we're going to make a dilution of that. So the dilution then is going to be giving us then a new concentration. So this is our working solution concentration. And of course, this is going to be our final volume. It's not the small volume of an aliquot, it's the final volume. This is our working solution, right? This is usually going to be larger than the aliquot than we started with. Okay, so this is, again, this is our stock solution, and this is our working solution. So the math is really straightforward. Let me just show you how the units cancel out. Well, actually, I don't need to show you how the units cancel out. But let's put the units in here. The units of molarity is moles per liter. Okay, so moles per liter in condition one, the stock solution, multiplied by the volume. That's the volume of the aliquot. That's going to be equal to the new concentration, moles per liter, in condition two, times the final volume. So the concentrations are different and the volumes are different, but what's the same? What's the same in both of these? Liters cancels out, liters cancels out. If you work out the math, you'll see moles are what's the same. The number of moles is equal to the same number of moles. The number of moles doesn't change. All we're doing is diluting the concentration. For this reason, stock working. So the number of moles are constant. So let me just show you a few examples of how you might see this in a word problem. And a lot of these come now in word problems. So you're going to have to start getting used to extracting the information you need from a word problem. So usually when I do these, I look for the information and then I notate down what I have on the left-hand side, just to kind of excuse the expression, take stock of what I have here. So what volume of 5 molar H2SO4, that's sulfuric acid, is required to make 4 liters of a 0.25 molar solution of sulfuric acid in water. So we're just making a dilution here. We don't really need to know that it's sulfuric acid. This could be anything. We want to know, we read this, right? What volume of one concentration is required to make a volume of a new concentration. So that sounds like it's a dilution problem. Of course it is, because we're working on a dilution slide here. So let's just take a look at what we have. Which one is the concentrated stock concentration? Is it this one? Is it 5 molar or 0.250 molar? Which is the stock? So I heard two things. The stock is 5 molar, right? The more concentrated is the stock solution. Now, let's just write this down. So M1 is going to be 5 molar, and V1 is equal to what? Well, that's what we're asked for. What volume? What volume of the stock? So this is our unknown. I'll just put a question mark there. We're going to solve for V1. When we do that, we're going to get a working solution concentration. That's 0.25. And our volume is 4 liters. Oops, sorry, that's V2. Volume is 4 liters. Okay? Now I know what I'm working with, and I have one unknown, thank goodness. I know how to solve for one unknown. Now let's go back to the relationship, and then we'll do some algebra. So the relationship is M1 V1 equals M2 V2. And now let's plug in what we know. Or you could rearrange this one and then plug in what you know. Sometimes it's easier to do that. Rearrange the variables first and then plug your numbers in. Since I have it very neatly organized, let's do that. We want to solve for V1. So we isolate V1. So we know that V1 is going to be equal to M2 V2 divided by M1. Now, we could put the units in for molarity and make sure that everything cancels out when you do algebra, but we can also just see we have molarity in the numerator and we have molarity in the denominator. So moles per liter, it's going to cancel out and we're going to end up with volume. All right, so the units cancel out appropriately. Now let's put our values in. M2 is 0.25. The volume 2 is 4. And the M1 is 5 molar. So now we should have our answer. So 0.25 times 4, so that's a quarter, times 4, that's 1. 1 divided by 5 should be 0.2, correct? 0.20. And its volume, this should be liters, which is the same as 200 milliliters if you wanted to work in milliliters. Okay. Why don't you try doing this last one? Does somebody have an answer? What'd you get? 0. What? 50. So 0.0050. All right. Anyone else get something different? I think that's the right answer. Let's make sure. So we're going to calculate the molarity of a solution made by diluting. So right there off the bat, we know we're working with a dilution. So I'm going to just write down my formula, M1V1 equals M2V2. Let's write down what we know and what we don't know. V1, M2, V2. So calculate the molarity of a solution made. So by diluting, we're going to take this amount of this molarity. The numbers are kind of strange because you want to think concentrated, that's a larger number, right? And diluted, I'm sorry, concentrated, concentrated is a larger concentration, go to a more dilute. But look at these numbers and you have to decide which one's larger, which one's not larger. Or just you need to match them up is really what you need to do. So we're going to dilute, that's your aliquot. So we're going to take, that's our volume 1, 0.050 liters. So the aliquot is always taken from the concentrated. So this is our stock solution, 0.1 molar. It looks pretty dilute already, but that doesn't matter. That's our starting. So 0.1. molar. Calculate the molarity, so that's going to be our new molarity, that's our unknown. And then the volume, it's the larger volume, it's going to be 1 liter. So now we know we're going to solve for M2. M2 is equal to M1 V1 divided by V2. M1 is 0.1 molar. We could put the molarity in here, that's fine. Let's put our units in. 0.1 molar. Volume 1, that's the aliquot, 0.05 liters, divided by V2, which is 1 liter. So it's going to be 0.1 times 0.05, which is 0.005 molar. Okay. So here's another typical molarity dilutions problem. We're asked to make 50 milliliters of 0.05 molar working solution from a 2 molar stock solution of calcium nitrate. Now notice I just, when we call this calcium nitrate, we've got 1 calcium for every 2 nitrate polyatomic ions. Don't forget those skills that we've been working on earlier about taking a name and figuring out what the compound is. And in this case, for an ionic compound, you need to know what the cation anion ratio is that gives you a net neutral formula unit. That's what this is, calcium nitrate. All right, so as I showed you before, let's take stock of the information that we're given in these word problems. We can see that it's a dilution problem because we're looking for keywords like stock solution and working solution. So even if it doesn't say in the problem that you're faced with that you're making a dilution, those 2 terms should key you in that we're doing this M1V1 equals M2V2. Honestly, for all my years as a working scientist, this equation, this manipulation, doing dilutions and doing this math, this simple ratio, I probably did this on a daily basis. This is probably the single most useful formula that any working bench scientist will do. All right, so let's take a look. We know we're looking for an M1 and a V1, our starting molarity and volume, and we're looking for an M2 and a V2. And reading through this problem, we have we're tasked with making 50 milliliters of a 0.05 molar working solution. So that's going to be down here. The volume is going to be 50 milliliters, and I'm just going to put that in liters. Okay, and the working molarity is going to be 0.05 molar. And what are we starting with? Well, we're starting with a stock solution of 2 molar. So here's our starting, and we're asked for this volume. That's the volume of the aliquot of the stock solution. What do we need to take from our stock solution and then dilute that into 50 milliliters of a working solution? So before I solve the math, though, let's just take a look practically at what we're talking about. So here's our stock solution that we've made. We've done all of our quality control and quality assurances. We know it's clean. We know that it's 2 molar, 2.0 molar calcium nitrate. And if we were to actually look at the ions swimming around in solution here, let's put those in as well. We've got calcium ions swimming around, and we have nitrate ions. Of course, we have many more than just these 3, but I'm putting 3 just to emphasize the ratio of cations to anions in this compound. These are present in a 1-to-2 ratio. And the concentration here, if we were to count these up and divide by the volume that it's in, we would have a concentration. There's 2.0 moles of calcium nitrate per liter. That's what the molarity symbol stands for. Now we're going to take some amount of that. We don't know what it is yet. That's what we need to solve. So I'm just going to take one little bit of that stock volume, and we're going to transfer it over here to our graduated cylinder. Okay, that's the aliquot. That's going to be our V1 of the stock solution that we're going to take, and we're moving it over to our graduated cylinder, and then we're going to bring this up to a final volume of 50 milliliters. because that's the dilution that we're making. So I move the aliquot over, and then I add some water to fill up that into the graduated cylinder up to the 50 milliliter mark. Okay, so here's our 50 milliliters. That's equal to 0.050 liters. And this is our working solution. Now we're done. Our working solution, we want that to be 0.05 molar. So the question is, what's the volume of that aliquot that we moved over to make all this happen? So this is what's happening visually. Mathematically, though, it's a simple ratio. It's the M1V1 equals M2V2. So we can write all of that in. M1 is 2.0 molar. V1 is our unknown, and that's going to be equal to M2V2 in our working solution. So the molarity, the diluted molarity is 0.05 molar, and that volume is in 50 milliliters, but I'm putting it in liters so that my units cancel out, because remember, the units of molarity is moles per liter. All right, so the math is now straightforward. V1 is equal to 0.05 times 0.05 divided by 2 gives me the volume of 0.00125. Now you need to be careful with your units. What's the unit on that 0.00125? It's liters. Now, typically, we're working with this graduated cylinder, which is measured in milliliters. So I would want to probably convert that into milliliters. That's 1.25 milliliters. Now take a look, though, at what's in that aliquot. What did we move over? Okay. In this aliquot, how many moles of calcium nitrate do you suppose are in that aliquot? Well, we can figure that out. Now we know what V1 is, right? V1 is 0.00125 liters. So how many moles is that? Well, we've got 0.00125 liters of a solution that's 2 moles per liter. That gives us, well, I don't need a calculator for that. That gives us 0.0025 moles of calcium nitrate. That's how much calcium nitrate was in that aliquot. I got that from M1 times V1. But what is it if we take a look at M2 times V2, right? This is going to be 0.5 times 0.5. What do you suppose that is? 0.5 liters times 0.05 moles per liter. That also gives us 0.0025 moles of calcium nitrate. Okay, the moles is the same. We're transferring that number of moles that we've got from the stock, and we're putting that into our final working solution. But the number of moles doesn't change. Number of moles is equal to 0.0025 moles of calcium nitrate. Number of moles doesn't change. Okay, you can do all sorts of things with this. We can also just focus on the concentration. We can focus now on the concentration of ions in solution. So in the working solution, for example, what's the concentration of calcium ions in the working solution? Well, or even in the stock solution, it doesn't matter. You can pick whichever one you want. So in the working solution, all right, that is 0.05 molar calcium nitrate. But what's the concentration of the ions themselves? For the calcium ion, the calcium 2+ ion, we have 0.05 moles of calcium per liter. Calcium, when this dissociates, 1 mole of calcium nitrate dissociates into 1 mole of calcium and 2 moles of nitrate ions, but we only have 1 mole of calcium ions here. Here, let me show that to you more formally. Let's do this. Let's not skip any steps. This is calcium nitrate. Right, and let's put another term in here that shows that for every 1 mole of calcium nitrate, that dissociates into 1 mole of calcium ions. All right, so if we do that math, well, that's just 1 to 1. So we know now that we have 0.05 molar concentration of just calcium 2+ ions, if that's what we were interested in. If we did this for nitrate ions, what do you suppose the concentration of nitrate ions are in the working solution?